Welcome to the Academic Express. Let's jump right in, because today we're exploring a concept that completely transforms how we look at the natural world. Those avian patients you treat every day in the clinic, or honestly, even just the pigeons outside your window, they are actually deeply modified, highly optimized theropod dinosaurs. We're going to walk through this explainer by looking at what the source material brilliantly frames as the great evolutionary retrofit.
Okay, to really get this, we've got to completely shatter an old misconception. The old way of thinking was this idea of a sudden, almost magical avian emergence. You know, like poof, birds just suddenly appeared with wings and feathers, perfectly ready to fly. But the new way, which the fossil record beautifully backs up, asks us to visualize this as a dynamic, millions of years long assembly line. It's a process where existing, ground-dwelling theropod parts were just ingeniously repurposed over deep time.
So, Chapter 1 of this retrofit begins with the foundation, feathers. Take a look at this incredible fossil of Sinosauropteryx. Notice those fine halo-like structures surrounding it? This perfectly illustrates that the very first feathers were not for flying at all. Actually, scratch that, they weren't even aerodynamic. These filamentous protofeathers were originally installed on the assembly line for thermoregulation, keeping these tiny dinosaurs warm and for visual display. This was millions of years before an aerodynamic airfoil was ever on the evolutionary blueprint.
Now, what's genuinely mind-blowing here is when you look closer at these ancient feathers, you find melanosomes. These are subcellular pigment-storing structures. And by looking at their exact shape, paleontologists had proven that these basal models utilized complex camouflage and display striping. So long before taking to the sky, these dinosaurs were vibrant, colorful creatures putting on a show with their non-aerodynamic fuzz.
And that foundation perfectly sets the stage for Chapter 2, where nature just went wild with aerodynamic wind tunnel tests. Enter Microraptor. This was a diminutive theropod that essentially tried to be a biplane. It possessed elongate pennaceous feathers not just on its arms, but literally on its legs as well. These gliding prototypes prove that flight was tested in multiple, highly experimental, and frankly kinda absurd-looking ways before the modern bird wing was fully dialed in.
Just look at the sheer morphological diversity of these early Paravian prototypes. With these different skeletal silhouettes, you can see wildly experimenting lineages. You had the bizarre Scansoriopterids testing out bat-like membranous skin wings instead of feathers, while others were testing out arboreal gliding mechanics. It was a massive evolutionary sandbox, rapidly iterating winged forelimbs long before sustained, powered flapping flight ever got off the ground.
All right, that brings us to Chapter 3, the internal overhaul. Because, as you know, having exterior feathers is just one piece of the puzzle. To achieve true mastery of the skies, this evolutionary assembly line had to completely redesign the internal skeletal machinery.
The real turning point in this internal overhaul is the divergence of a massive group called the Ornithothoraces. Think of this split like two rival manufacturing lines. On one side, you've got the Enantiornithes, the opposite birds. They absolutely dominated the Cretaceous skies, but they still held on to primitive features like teeth and clawed fingers. And on the other side, the Ornithuromorpha. These were the heavily upgraded, incredibly streamlined ancestors of all modern birds.
So to outcompete those rival models and get that unparalleled aerial maneuvering, a major change had to happen. The heavy, balancing theropod tail had to be decoupled from the hind limbs. Notice how the tail here shortened dramatically and fused into this plowshare-shaped bone, the picostyle. This was a huge upgrade. It allowed the heavily modernized ornithuromorphs to anchor a highly controlled rectricial tail fan, which basically functions exactly like the rudder and elevator system on a modern aircraft.
Concurrently, the chest cavity got a massive retrofit. A progressively deeper keeled sternum was installed to anchor the massive pectoralis muscles, literally the engine of flapping flight. And right alongside this, the trioceal canal evolved. This is a dedicated, bony pulley system at the shoulder that effortlessly elevates the wing during the upstroke. It's an absolutely crucial piece of engineering for sustained flight.
But you know, perhaps the most surprising retrofit of all is the respiratory system. It is so vital to recognize that the hyper-efficient unidirectional airflow system, the one utilizing flexible air sacs to provide a constant stream of oxygen during both inhalation and exhalation, actually predates flight. It was inherited directly from their dinosaur ancestors. The assembly line literally just took an existing, highly efficient dinosaur respiratory engine and perfectly repurposed it for the extreme metabolic demands of flying.
Let's move right into Chapter 4, where we witness the systemic weight-saving overhaul.
As you know, flight demands absolute minimum weight. So over millions of years, those heavy reptilian jawbones and teeth meticulously phased out. In their place, a lightweight, highly adaptable keratinized beak was installed. And to process food without those teeth, they developed a specialized crop for storage and a muscular gizzard for grinding, completely bypassing the need for a heavy head.
Plus, the internal reproductive system underwent a brilliant weight-reducing retrofit of its own. The right ovary was entirely shut down. I mean, talk about an extreme weight loss program for an egg-carrying aeronaut. Shedding half of your reproductive plumbing is just a genius aerodynamic move. And this isn't just a theory. This early modification is strikingly evidenced by fossilized ovarian follicles we've found in early birds, proving these specific trade-offs have incredibly ancient roots.
So watching this timeline unfold, the whole picture just beautifully comes together. You have Sinosauropteryx's insulating fluff, Microraptor's experimental gliding biplane, Archaeopteryx's early flapping flight, and Ichthyornis' derived near-modern anatomy. All of these disparate parts gradually coalesce into a completed, harmonized flying machine. It didn't happen overnight. It was an incredibly slow, meticulous retrofitting of a terrestrial predator into an absolute master of the air.
For those of you in the clinic right now, your takeaways from this explainer are actually quite profound. It's about constantly acknowledging this deep dinosaurian homology in your daily work. When you're treating these animals, remember that their pre-adapted respiratory efficiency, their incredibly fragile skeletal modifications, and their unique reproductive constraints aren't just random quirks. They are ancient, meticulously crafted aerodynamic trade-offs.
Because the truth is, evolution never shuts down its assembly line, which leaves us with one really profound question. As our world rapidly changes today, what invisible retrofits are happening in the DNA of birds right now? Thank you for exploring the great retrofit with me in this explainer. Keep your curiosity alive, and as always, keep looking up.